Thanks very much, Sam, and thanks very much for having us up here in this an interesting new format. STEAM is the shortened version of the long project title you can see here. I'm not going to talk you through it other than to say that we got this funding from a research call to do with decarbonising the grid. So it's a research call around grid scale energy storage. So although we're talking about storing thermal energy, we're really talking about storing thermal energy as a service to the electrical grid. And as Sam said, it's collaboration between Strathclyde and Edinburgh. We've got a large part of the delivery team here giving talks, other bits of the delivery team peppered through the room. So what's the kind of the philosophy behind STEAM? The idea is that when renewable energy is intermittent, when we have too much energy in the grid, we pay the renewable energy companies to turn off the turbines. And in East Ayrshire alone, we don't generate 120 gigawatts a year that we could generate. And that costs all of you as customers about £40 a year on your gas bills to pay those curtailment fees. What we want to do is to take that energy, not turn the wind turbines off, use that energy to heat up water in a mine shaft, not in a mine workings, but in a mine shaft. And if we can take it to 55 degrees, then on a no wind day, we can take that heat straight out, put it into a heat network without the electrical demand of a heat pump. So we're sort of reducing the peak there. Now there's all these ifs. If we could use 1% of the mine shafts in the UK to do this, and if we could take those to 55 degrees, then in a week when there's no wind in the middle of winter, what's called a worst case weather week, we could heat 10% of the UK's homes for 1 week. So the opportunity is huge, but so are the ifs. So what the STEAM project is trying to do is to reduce the uncertainty on some of those ifs. We want to check whether my 1% figure I made it up for the proposal, but is it reasonable? And the answer is sort of. Is it structurally safe? So that's what we'll be talking about that. Is 55 degrees going to create any problems with the water? Indrani will be talking to us about that. Where will the heat go? Jessica will be talking about that. How does that plug into the grid? How does that work in the energy system? And that's Bryn Eng at the end. But finally, here's our work packages. Finally, my work package that I'm leading is to actually do it. As we've heard a number of times this last couple of days, we want to be doing stuff. We don't want to be modelling stuff. So fingers crossed, if a whole load of dominoes fall into place, later this year, we will be injecting heat into a mine shaft just south of Edinburgh. Tamrock Energy are our subcontractors who will have designed the experimental setup. We're not going to talk about that today, but if anybody wants to know more about that experiment, come and ask me after coffee. But without any further ado, I will pass you on to the people who are doing the real work so far. And first of all, we have Indrani telling us about the chemistry.
Good afternoon, everyone. My name is Indrani Mukherjee, and I'm working on work package 1. So, what is the purpose of soft water assessment? Storing heat in soft water can alter the geochemistry of the soft water. It can disturb the equilibrium condition of the soft water. It can dissolve more mineral from the shaft wall, or it can change the water phases. And these chemical changes with increased temperature can cause clogging, scaling, corrosion, or even thermal breakthrough. So, therefore, it is necessary to analyze and model these chemical changes with increased temperature to understand the feasibility of mine shaft thermal energy storage. So, as a case study, we are aiming to inject heat in Moncton Hall Shaft 2, situated in the Midlothian County, through a closed-looped steel U-tube. And this Moncton Hall shaft is concrete lining, and the water level varies from 19 to 22 meter below ground level. And during the closure of this mining, it was backfilled with basalt up to 280 meter below ground level. So for the initial chemical data, we can say that water is in reducing condition, and some suspended iron present in the form of ochre, and dissolved iron mainly present in the form of ferrous iron. And the pH is circumneutral, and the chloride and sulfate concentration is higher than the bicarbonate concentration, so we can say that the water is corrosive in nature. The water type is calcium, magnesium, sulfate water type, and for as per recent data, we can say the temperature varies between 11.4 to 11.5, and conductivity varies from 930 to 980 microsiemens per semi up to 100 meter of depth. So Frick modeling was performed with 5 degrees Celsius increment of temperature from the initial measured temperature, which is 12.1, up to 85 degrees Celsius, to evaluate the chemical changes with increased temperature, how the chemistry is changes, and is there any ochre or scaling will form or not. And here we used the standard cement composition for this modeling. So as per Frick result indicate, we can say that pH varies with temperature, but within circumneutral range. You can say that calcite is oversaturated and will be precipitated. And the concentration of sulfate and chloride did not change with temperature change when comparing with bicarbonate concentration. So the corrosiveness nature of the water remain same. If we see the scaling, so we can say that the chances of scaling is increased slightly after 52 degrees Celsius from the initial temperature, but the changes are not that significant, because from the initial temperature, that is 12.1, up to 52 degrees Celsius, the calcium precipitation decreased by 0.96%, and after 52 to 85 degrees Celsius, the calcite precipitation increased by 1.3%. So we can say that the chances of scaling is minimal. So what about the ochre formation? We know that ferric oxyhydroxides are quite insoluble at neutral pH and normal temperature. And here, for the Frick modeling, we assume that there are no further exposure of atmospheric oxygen. And Frick model result shows us that all the iron compounds are undersaturated or close to the equilibrium line. So we can say there are no significant ochre will form if unless this is exposed to atmospheric oxygen. So for the key points, we can say that pH increases with increased temperature, but within the circumneutral range. Calcite will precipitated, but in a minimum scale will form, and there are no significant ochre will form, and still the water is in reducing condition. Thank you.
Hello everyone, I'm Huachuan Wang. My research mainly focuses on the steam workbench 2, the structural safety for legacy mine shafts submarine storage. And we know that the legacy mine shaft is a promising structure for submarine storage. However, it is reported that there are on average 15 mine shaft collapses occurring in UK every year, which means that not every mine shaft structure could be safely used for the submarine storage due to the structural degradation. So which brings us about 3 key questions. So whether legacy mine shafts are safe to be used before the submarine storage, and whether these structures are safe or not during submarine storage operation, and how long these structures can be used for the thermal storage purpose. So in order to answer these questions, the 3D numerical modeling was conducted on the multi-hole number 2 mine shaft and the Barney number 3 mine shaft as case studies. And we take into account the shaft diameters, like the shaft geometries, like diameter, thickness, the depth, water level, and stratigraphy into our model. And the numerical simulation results before the thermal energy storage shows us that the structural stress increases with the shaft depth, and it also is affected by the weak rock layers, like the coal seam and the fault zone, which means that the structural stress status will be highly dependent on the shaft depth and also the stratigraphy. And when the landing material strength decreases due to the degradation, the risky region of the structure could expand from the bottom, which means that the landing material properties would be very important for the structural safety. However, we are still not clear about the current status of the landing material. And during thermal energy storage, for example, as an open loop storage scheme, the water level would change during the thermal water injection and extraction. The structural stress shows that the structural stress reaches the maximum in case 2, where the shaft is empty, but the minimum stress could be achieved in case 1, when the internal water level equals to the underground water level. So, which means that the water inside the shaft can actually help the mine shaft to achieve to balance the structural stress and to help with the safety. So, which means that the closed loop scheme is relatively safer than the open loop scheme in terms of the structural safety. However, when we take into account the operation surface life, the question could be more complicated. For example, during thermal energy storage, the water level change could cause the cyclic water pressure on the structure, and the temperature fluctuate, for example, from the 15 to 55 degree, which will cause the thermal stress of the structure. And also the chemical ions like the sulfite in the mine water would also cause the corrosion of the landing materials. And these factors would interact with each other. For example, the water level change would affect the heat transport and ion migration. And the temperature fluctuation could accelerate the reaction rate of the corrosion process and also affect the water pressure. So which means that this factor interaction would further accelerate the deterioration of the landing materials and also result in the reduction of the service life. So, give a brief summary, there are still some challenges to be considered and to be solved. For example, we are still not clear about the current status of the structure and the concrete in legacy mine shaft, and we are still have no idea about the material deterioration process under the multi-physical environments. Also, the durability and service life of the structure need to be further investigated. So correspondingly, we need to do the set investigation like the CCTV camera and also the concrete sampling, and also we need to lab test to know more about the status of the legacy mine shaft structure and materials. And also we are establishing a multi-physical experimental system to replicate the real thermal energy storage environment and also to investigate the deterioration process of the landing materials. And finally, based on the experimental data, we can further calibrate our numerical model to better predict the service life of the legacy mine shaft structure. Thank you.
I'm Jessica Dasso, and I'm going to present my work on the package number 3. So, what is our work package going to do? We want to assess the potential of mine shafts for heat storage. So basically, we want to answer these questions. How fast can we heat up the shaft? And this will be especially interesting for our upcoming pilot study. And how quickly does the shaft lose this heat? What does thermocyclic heating and cooling do to the heat storage? And how much detail does our model have to answer these questions? So as mentioned before, we'll run a pilot soon. And for example, for our model, we need to make some first decisions here. Like, what is the heat source and how do we implement that? And for our for this model that I'm presenting, we have to make a few assumptions, like the heat storage coefficient. Here it's H, which is assumed to be constant. So from that, we build up our first model, which couples the turbulent flow in the shaft with the heat transfer all over the area. So this includes the rock and the shaft and its lining, and all the modeling is done in COMSOL. And for the turbulent flow, we use a Reynolds average Navier-Stokes model. So this is a bit of a busy slide, but it's just if you're interested in the model setup, we need to make we need to set the initial and boundary conditions, and most of them are from literature values or calculated or from smaller models, because as we learned from other presentations, often data aren't available. So for our model, we assume a homogeneous rock, which you can see in yellow on the left, and the water body is in blue, and this is sort of a slice of a cylinder, so it's a radial symmetric approach to save some computing time. So basically what we get out of this is a 3D representation, so this will form a cylinder later on. Oh yeah, and the heat source we're going to use is an implemented heat flux boundary, which will sit 50 meters below the surface as a sort of line heat source. And for this setup, we only model 14 days to see how fast we heat up the shaft. So let's have a look how the shaft heats up. On the left, you can see the temperature slowly increasing. The hot water is rising to the top, so you can see the hotter surface. On the right is the velocity field in white as the little streamlines. They show the direction of the flow. And the color bar is the velocity magnitude, so you can see how fast the water flows, and you can see how the water along the heat source is quickly flowing up, heating up to the surface, and cooling down on the surface and flowing down on the cold walls of the shaft. So after 14 days, this is the same figure as before, basically not a video now anymore. We can look at the average temperature of these top 50 meters of the water. And you can see on the right that we probably, with the assumptions we made in our model, we will heat up the shaft by 20 degrees. And we can also let the whole system cool down. If we turn off our heat source, then you can see in green how the cooling down is happening. So we lose around 5 degrees in those 14 days. So much slower than our heating up, which is what we want, ideally. We have other models, for example, this one, which shows the groundwater flow coupled to the heat transfer. So for this model, we ignore the fluid dynamics, but ultimately we want to couple all of it into one big model. And we need to do a lot of sensitivity studies on that. For example, the dip or width, how is that influencing our heat storage? And I'll present a quick example on the shaft lining thickness influencing the heat distribution in the model. So for this one, we have a 3D setup now, and we introduce a hydraulic gradient, which we didn't have before, and a constant wall temperature of 40 degrees as our heat source. And now we look at 50 days. And what you can see here is how the groundwater velocity carries the heat away. So on the left, you can see the groundwater flow changing around the cylinder structure of the shaft. This is an upwards view of the model we just saw. And on the right, you can see the temperature sort of smearing in the direction of the groundwater flow. And if we now take a slice of that and look sort of in the middle or anywhere else in any depth, what that does to the local temperature distribution, you can see that the shaft lining influences this temperature actually a lot. So if we assume we don't have any lining in our model, then we get almost a 10 degrees difference to the 1 meter lining. But probably our shaft will have a lining between 0.5 and 1 meter. So we are probably around a difference of 5 degrees locally for this example. So to summarize this, we had a quick look at 14 days of heating, and we also had a look at 14 days of cooling, which is much slower. And for our model, for a quick sensitivity study, we showed that the lining is quite important to be included in our whole model. That's it.
So good afternoon, everyone. My name is Vinyan Yu. I'm from the Energy Research System Unit, University of Strathclyde. So I'm working in steam work package 4 with Portugal and Grand Flat. Today, my topic is the value propositions for the mineshaft thermal energy storage in district heating and future wind-based grid balancing. So, to integrate the energy systems in terms of electric, heat, and control, objectives go out to identify the value opportunities for the key performance indicators for the mineshaft thermal energy storage. And second is to develop and validate the model, to conduct the whole system modeling for the case study sites, and analyze the techno economics. Here shows our mineshaft thermal energy storage system with heat pump diagram. The main components of the system are the grid, heat pump, post-electric heater, store, and district heating network. In our research, we took West Willowburn district heating network as our study case, which consists of 1,632 dwellings with around 10 GWh per annum and 4.2 MW peak. This slide shows our heat pump mineshaft thermal energy storage operation using the fixed order controller. The main objective is to maximize the usage of the grid load tariff. Here, the store is filled when the price is low and discharged when it's expensive. In our research, we carried out concept screening study that involved the parametric, combinatorial study, and optimization to determine the best combination of the parameters for the best case. By comparing the results for 3 days in winter, for the base case scenario for 30 degrees Celsius, 200 meter store with heat pump, the system will use the grid high tariff due to the use of the secondary heat pump to meet the heat demand during the low wind periods. However, for the high temperature store scenario at 70 degrees Celsius, the use of grid high tariff can be avoided due to the store can direct feed to the 50 degrees Celsius heat demand during the low wind periods. But the surrounding ground temperature will be heated much higher than the lower temperature store. And for the grid balancing, the high temperature store with the heat pump is the best, and around 99% of the total electricity will use the grid load tariff. For the levelized cost of heat, the best case falls at the 70 degrees Celsius store with around 70% reduction in levelized cost of heat, and in our research, the OPEX has higher influence than the CAPEX. Okay. For the store efficiency, the 70 degrees Celsius 400 meter store has around 84%, which is lower than the smaller and lower store temperature case. The reason is the higher heat loss occurs from larger and or the higher temperature store. So in summary, the optimum mineshaft thermal energy storage system is 70 degrees Celsius store temperature, 400 meter store using heat pump. This system has a levelized cost of heat of 3 pence per kilowatt-hour, 99% of total electricity use grid load tariff, and 60% of store heat loss. And in future development, we will investigate in the combined heat and power-based mineshaft thermal energy storage system. And to balance the grid, the system will export when the price is high during the low wind periods. So lastly, I'll leave you with an overview of all our presentation from each work package of the STEAM project. Thank you so much for listening.